Let's do some calculations for our example with Wade and Riebe. Let's recall that which statistics we already have. We have the average, we have standard deviation and the sample size. And then I will just round the values to one decimal. So the average for Wade was 152.1 milligram per liter, and then for Riebe it was 139.3 milligrams. The standard deviation is 9.3 for a sample from Wade and 9.9 for the sample from Riebe. And then the sample size is 10 and 10. Now, first of all, let's calculate the standard error. You remember that standard error is S over square root of n if we have one sample t-test, right? So it means that in this case, in the first case, it will be for Wade. It will be 9.3 over square root of 10, which gives us approximately 2.94. 2.9. Okay, and for Riebe, it will be 9.9 over square root of 10, which is approximately 3. So in this case, I will use 2. So we can write that this is 2.94, this is 3.13, this is standard. We also denote standard error as a standard deviation. Now let's make a t-test. Let's say that we would like to know if our rivers are contaminated or not, and then let's say that the average chloride content for the river not being contaminated should not exceed 146. So our null hypothesis is that the rivers are not contaminated. So the average chloride content in all rivers, in the whole rivers, does not exceed 146. Okay. So first of all, we have to calculate how big the difference, how extreme the difference between the average of sample and average of population, as we assume about that, is. We use the t-values for that. So let's calculate t-value for Wade. We take 152.1 minus 146. And then it's over the standard error, right? So we know already standard error. It will be 2. Then for Riebe, the t-value will be 139.3 minus 146, and then we divide it to 3. So we can use just calculator to find out the values. It will be 2.07 for Wade and minus 2.14 for Riebe. Now, how to find out if these values are extreme or not? Okay. Let's recall what the null hypothesis is. This is our null hypothesis. So this means if we have, for example, this is our t-distribution for 9 degrees of freedom. For 9 degrees of freedom, here we have 0, we have 1 here, 2 here, then we have minus 1. Now we can draw it like this, approximately. These are all possible t-values for the given degrees of. Now, if we take the first t-value at 2.07, so we have it here. So 2.07 is, so this is t for Wade, right? T for. And then the second is minus 2.14, so it will be here, which is a t-value for t-value. Okay. So now, which of these two values is extreme? Let's think. Our null hypothesis that mu is 146 or even less, right? So it means that the extremeness is getting in this direction. So as soon as sample average will exceed the average that we assume our population has, it's 146, the sample become more and more extreme. And then the bigger difference between the sample average and the population average is, the more extreme the sample is. It means that the p-value should get smaller in this direction. So it means that we have to use the right tail. Okay. So for the Wade, the p-value will be this area, and you can see that it's quite small. So it means that it seems like for Wade we cannot accept this null hypothesis. Of course, we have to calculate the real p-value. We will do it in a minute. But for Riebe, this is the p-value, okay, and it seems to be quite okay. So it seems like we cannot reject null hypothesis for Riebe. Now let's see how to do that. first of all, I will show you schematically how this distribution is, and then where do we have this the values, and then we will calculate the probabilities using CDF function for t. So let me start with making a plot for t distribution for the density of t distribution with nice degrees of freedom. So I first generate a sequence of t values. Sequence. I will start from, for example, -3, and then I will end with 3. It's enough. Our t values will be inside. Then I will generate, let's say 100. So we have a smooth curve. And then for every t value, I will calculate density. Which will be the density for t distribution. I have this t value, so for every t value I will get the density, and then it's 9 degrees of freedom. And then I can make a plot, t versus density. I will make it a line plot, and let's use it. So let's make this. Now look, this is the distribution, and you can see that it goes from -3 to 3 approximately, right? And then this is where we have Wade, and this is where we have Riebe. Let's add horizontal lines to this plot, corresponding to the t values, AB line. We have vertical line, and then for Wade we have 2.07. And then AB line, vertical line. For Riebe we have -2. So that's the new plot. And then I will also add a line for the 0, so you can clearly see where the 0 is. So that's the plot. Look, so for Wade, the probability to get a sample as extreme as Wade, or even more extreme, assuming that null hypothesis is true, it's the area on the right, this one, and it seems to be quite small. We will calculate it. But for Riebe, the probability that as extreme as we have, or even more extreme, assuming that null hypothesis is true, it will be all this area. And then we use CDF function, because now we use the right tail. We have to use CDF function and then subtract it from 1, because CDF function always gives us an area on the left. So that's the p-value for Wade. P-value for Wade is 1 minus the CDF function in R is p function, so it's CDF function for t. Then I use the t value we found for Wade. It's 2.04, and then the 9 degrees of. So let's show the p value. So if we calculate it, we get 0.36, which means that 3.6% chance to get a sample as extreme as ours, or even more extreme, if null hypothesis is true. Okay, so it means that if Wade River is not contaminated, only 3.6% chance to get a sample like we have. Okay, so you can think that 3.6% chance that our sample came from non-contaminated. And in this case, of course, the chances is very small, because contamination of river is can be very dangerous. And in this case, we have to reject. But if we do the same for Wade, we take the same CDF function, but now we use this t value for Wade. It's 1.14, and then 9 degrees of freedom. Look, for Wade, the p-value is very small, 97. So it means that 97% chance to get a sample like we have, or even more extreme, if river is not contaminated. And it seems to be so. So we do not reject null hypothesis in this case. So we assume that Wade is contaminated and Riebe is not.